The last two beta-lactam classes that we will be covering in this lecture are carbapenems and monobactams. We'll start first with carbapenems. Now, thionomycin was the first isolated compound that had a carbapenem pharmacophore. In a carbapenem, relative to the penam in penicillins, the sulfur is substituted with a carbon, and it has a double bond linkage between carbons 2 and 3. Thionomycin had the best qualities desired in an antibiotic, an extraordinarily broad range of activity against gram-positive and gram-negative bacteria, including Pseudomonas aeruginosa, and high stability against the deactivating beta-lactamases. Comparison between the penam and carbapenem rings indicates a higher ring strain in carbapenems, which leads to increasing the electrophilicity and consequently the reactivity of the beta-lactam. The two factors contributing to the increased ring strain are having a carbon instead of a sulfur at position 4 and the double bond. Carbon, relative to the sulfur in penam, is half its size, which adds more strain to both the 5-membered and the beta-lactam rings. The endocyclic olefinic bond that connects carbons 2 and 3 is shorter than a single bond. Other differences that distinguishes carbapenems from penams and cefams is the trans-relative stereochemistry of the substituents on the alpha and beta carbons of the beta-lactam. The alpha carbon of the beta-lactam lacks the acyl imido and has a hydroxy ethyl instead. This substituent with an alpha configuration that is opposite to what is seen in penicillins and cephalosporins is thought to play a major role in carbapenems beta-lactamase resistance. Thionomycin, along with all FDA-approved carbapenems, are poorly absorbed from the GIT. The reasons behind the bad oral bioavailability includes instability in gastric fluid, poor membrane permeability, and intestinal secretion by secretory transporters. Despite the excellent activity and stability of thionomycin against beta-lactamases, there were few drawbacks that necessitated optimization. First, it was chemically unstable. This instability resulted from the primary amine. This basic primary amine, when not protonated, is considered strongly nucleophilic, thus attacking the electrophilic beta-lactam in another molecule, leading to its inactivation. This problem was solved structurally by transforming the primary amine in thionomycin to the more basic amidine, as seen in imipenem. Imipenem is much more stable because the percent of molecules protonated at equilibrium would be more, which means that less neutral nucleophilic imipenem molecules that are responsible of deactivating the beta-lactam are present. The other issue that was also associated with thionomycin as well as imipenem is metabolic instability against dehydropeptidase 1. Dehydropeptidase 1 is an enzyme found in renal brush borders. It binds to thionomycin and imipenem, which are excreted by glomerular filtration and tubular secretion, breaking the beta-lactam, thus deactivating the drug and consequently leading to nephrotoxicity. This issue was primarily solved by co-administration of an inhibitor of this enzyme, which is cilastatin. Meanwhile, structural optimization of imipenem was underway so as to have carbapenems that are intrinsically resistant to dehydropeptidase 1. Structure-activity relationship studies have resulted in the finding that a beta-methyl on carbon 4 prevents hydrolysis by dehydropeptidase 1. Thus, the carbapenems you see in here, meropenem, doripenem, ertapenem, which are FDA approved, and the investigational tipipenem bivoxyl, can all be administered as single agents. Ertapenem has an ionizable benzoic acid group, leading to high protein binding, thus having a long half-life that allows for once-daily dosing. Carbapenems are considered the beta-lactams with the broadest spectrum of activity, thus they are amongst the most researched antibacterials. Tipipenem bivoxyl is one of many carbapenems being developed. It's an investigational prodrug that is still under preclinical studies. The bivoxyl was added for the purpose of enhancing the membrane permeability, thus its oral bioavailability. Let's move on now to monobactams. Sulfazesin was among many monobactams isolated from nature. It showed excellent resistance against beta-lactamases, obviously due to the alpha-methoxy on carbon 3, yet it was weakly active. Thus, this monobactam underwent extensive structural modification to optimize its potency. The SAR studies, based on the vast number of analogues prepared, showed that the alpha-methoxy, though essential for stability against beta-lactamases, it contributed to the low antibacterial potency and the poor chemical stability of these antibiotics. Thus, it was removed in later analogues. The loss of resistance against beta-lactamases due to the removal of carbon 3-methoxy was compensated for by having a substituted enzyme on the amide side chain. Azithromycin, shown in here, was the first FDA-approved monobactam that has a side chain closely resembling that of ceftazidime. Another structural feature in monobactams that contributes to increasing stability to beta-lactamases is a methyl on carbon 2. This methyl was also found to increase activity against gram-negative bacteria. Azithromycin and other monobactams, such as tigomonam, have shown that a fused ring with the beta-lactam is not essential for activity. The strain added by the fused ring in penicillins, cephalosporins, and carbapenams that results in increasing the reactivity of the beta-lactam towards the transpeptidases is compensated for by the stabilizing effect of the electron-withdrawing sulfonic acid and sulfonated groups attached to the amide's nitrogen. The sulfonic acid and sulfonated groups accounts for the essential ionic interaction that the C2 carboxylic acid, seen in all previous beta-lactam classes, forms with the active site of penicillin-binding proteins. Now, though the sulfonic acid in azithromycin, for instance, is connected directly to the nitrogen, while the carboxylic of the previous beta-lactam antibiotics such as penicillin G is connected to carbon 2, yet the large size of the sulfur atom sufficiently spatially resembles the corresponding C2 carboxylic group. Azithromycins and tigomonams side chains resembles those seen in third-generation cephalosporins, which leads to increasing stability against beta-lactamases and affinity to many penicillin-binding proteins isoforms, such as penicillin-binding protein 3 expressed by many gram-positive and gram-negative bacteria. The methyls on carbons 2 also contribute to enhancing the stability against beta-lactamases. Azithromycin is a parenteral beta-lactam. It's not orally active, mostly because it's acid-labile. The structural modification in tigomonam that resulted in enhancing its acid stability, thus oral activity, was converting the sulfonic acid to sulfate, or in other words, inserting an sp3 hybridized atom between the nitrogen and the sulfonic acid sulfur. The explanation of the variations in acid liability to hydrolysis between the two monobactams can be well understood by looking at the effect of the sulfonic acid and sulfate groups in azithromycin and tigomonam respectively. Upon cleavage of the azithromycin's beta-lactam, the developed charge on the nitrogen can be stabilized via both the inductive effect of the electron-withdrawing atoms and via resonance, while in the case of tigomonam, the group withdraw electrons inductively only, which means that the beta-lactam of tigomonam will be less liable to hydrolysis in acidic conditions, thus orally active.